Hello everyone. In today's lecture, we'll continue our journey with Laplace Transform. In the previous lecture, we've learned that the objective of Laplace Transform is to represent any arbitrary signal x of t as a weighted superposition of the complex exponential e to the power st. And we've also shown that e to the power st is an eigenfunction of the LTI system, and the corresponding eigenvalue is h of s. h of s being the Laplace transform of the impulse response, h of t, and it's also known as the system transfer function or the system function. And we've also seen that there are two types of Laplace transform: unilateral Laplace transform and bilateral Laplace transform. In today's lecture, we will talk about the unilateral Laplace transform. As a matter of fact, there are many applications of the Laplace transform in which it's reasonable to assume that the signals we're dealing with, x of t or whatever signal we're computing Laplace transform for, these signals can be assumed to be causal. And by causal, we mean that these signals have zero value for time less than 0. Again, let me remind you, causality is a description or a property of a system rather than a signal. But here, when we describe a signal as being causal, we simply mean that if this signal is an impulse response of a system, the system would be causal. Given this, a causal signal is simply a signal whose values are 0 before t equal to 0. So for t less than 0, the signal has to be 0. In this case, we can use the unilateral or the one-sided Laplace transform, which is based only on the non-negative time, that is t larger than or equal to 0. So time t equals 0 is included in the unilateral Laplace transform calculations. By working with causal signals are right-sided signals. They start at t equals 0 up to infinity, so they are right-sided signals. And as we have seen in the previous lecture, right-sided signals would have a right-sided region of convergence starting at the rightmost pole extending to infinity. So working with causal signals would remove the ambiguity in the bilateral transform. That's the need to have a region of convergence. As we have seen in the previous lecture, in the two examples we had, we needed to define a region of convergence. We had to say this expression for x of s is valid for this region of convergence. But here, working with unilateral Laplace transform with causal signals, the signals will be always right-sided, so the region of convergence will always be right-sided starting at the rightmost pole extending to infinity. In other words, we do not need to specify the region of convergence for the unilateral Laplace transform. Also, the differentiation property of the unilateral Laplace transform is very useful to analyze the behavior of causal systems described by differential equations and initial conditions, and we're going to see many examples on this situation where we have a system described by differential equations with initial conditions, and we use the Laplace transform in order to simplify the system analysis and get the system properties. So the unilateral Laplace transform of a signal x of t is defined as follows: integration from 0 minus up to infinity of x of t e to the minus st dt. This 0 minus means we will be integrating just before the 0, which means if we have an impulse at 0, this impulse will be included in the integration. So the lower limit of 0 minus implies that we do include discontinuities and impulses that will occur at t equals 0. So x of s will be, as a matter of fact, depending on x of t for t larger than or equal to 0. So 0 is included in this integration. The inverse unilateral Laplace transform will be given by the same equation we have seen in the previous lecture, 1 over 2 pi j integration x of s e to the power st ds, which is a complex integration, would be evaluated using the residue theorem. We will not be going through it right now. We will be doing the inverse in a different way. We will use a different approach to compute the inverse Laplace transform. So we will denote this transform pair as follows. So x of t has a unilateral Laplace transform, so we have this L lowercase u, and will give us x of s, where Lu, this u denotes the unilateral transform. Naturally, the unilateral and bilateral Laplace transform are equivalent to each other if the signal x of t is 0 for t less than 0. So if we have a signal x of t whose values are 0 for time less than 0, then computing the unilateral Laplace transform, which is integrating from 0 minus up to infinity, will be equivalent to the bilateral transform, which implies the integration from minus infinity to plus infinity. Next, let's talk about the properties of the unilateral Laplace transform. The properties of the unilateral Laplace transform are similar to those of the Fourier transform. I know we did not study Fourier transform, but when you study Fourier transform, you will see a great similarity between the properties of the Laplace transform we're going to see in this course with the properties of the Fourier transform. The properties described here specifically applies to the unilateral Laplace transform. The unilateral and bilateral transforms have many properties in common. Many properties are similar for the unilateral and bilateral transform, although there are some important differences which will be discussed going through this chapter. So, in these properties, we will assume the following. We will assume we have a signal x of t whose unilateral Laplace transform is x of s. And we will assume a signal y of t whose unilateral Laplace transform is y of s. So, the first property we have is very simple. It's called the linearity. Given that we have x of t with the transform x of s, y of t with the transform y of s, what if we have a linear combination between x of t and y of t? So you have a constant times x of t plus another constant times y of t. This is called a linear combination of x of t and y of t. So, in time domain, if we compose a new signal, which is basically a linear combination of x of t and y of t, the unilateral Laplace transform would also be a linear combination of x of s and y of s, using the same constants. So, a x of t plus b y of t would give a transform a x of s plus b y of s, which means the unilateral Laplace transform is a linear transform. You can decompose the signal to be transformed into simpler components, compute the transform of every component independently, separately, and then add the components together. This will give you the equivalent or the resulting unilateral Laplace transform. So, the linearity follows from the fact that the integration, which is the definition of the Laplace transform, is a linear operation. The integration of ax plus by is simply integration of ax plus the integration of b times y of t. And this will help us actually doing the inverse Laplace transform and doing some problems in the Laplace transform. If you have a function defined as this plus that, you can find the Laplace transform of the first term, find the Laplace transform of the second term, and then add them together. Doing the inverse, same way. If you have a certain Laplace function x of s and you want to inverse and find x of t, in this case you can express x of s as a summation of some terms. You can do the inverse for every term individually and add them in the time domain. So linearity actually is a very, very useful property. Second property is a scaling property. If you remember, in the first chapter we had discussed some operations which can be performed on signals. One of them was a scaling operation, where we had x of at, so x of 2t or x of t over 2. This represents sort of scaling, compression or expansion in the time domain. So the property simply says that x of at will give us in the s domain 1 over a x of s over a. This is for a larger than 0, for positive values of a. In other words, this property does not include the time reversal part. Of course, the time reversal part will make a big problem here, because the integration of the unilateral Laplace transform goes from 0 minus up to infinity. So if you do a mirroring or a time reversal, the situation will be completely different, and the signal will be shifted or moved, or it will be mirrored into the negative time. It will be a problem. So A must be positive over here. So this property implies that if you have a compression in time domain, you would be having expansion in S domain. Or if you have expansion in time domain, you would get a compression in the S domain. So the scaling in time domain introduces the inverse scaling in the S domain. Here in the time domain it's x of at. Here in the S domain it's x of s over a. So the scaling property implies this inverse scaling relation. And this inverse relation actually applies also to the Fourier transform. So a compressed signal in time domain would result in an expanded signal in S domain or frequency domain, and the other way around. The third property we have over here is the time shift property. It simply says that if we know a signal x of t whose unilateral Laplace transform is capital X of s, then the unilateral Laplace transform of x of t minus tau, which is a time-shifted copy of x of t, would be the same x of s multiplied by e to the minus s tau, where tau is a time shift happening in time domain. So x of t minus 2 would give us e to the minus 2s times x of s, and x of t plus 3 would give us e to the positive 3s times x of s. But here we have a problem. Remember that in the unilateral Laplace transform, the integration starts at t equals 0 up to infinity. So shifting the signal in time domain might cause a problem. We might have a non-zero part happening before t equal to 0 shifted to t larger than 0, or the other way around. A non-zero part of the signal which was happening at t larger than 0 being shifted before 0. These two situations will affect the integration, and hence this property will not apply. In order to understand this, let's move to our whiteboard and see how it goes. So let's first talk about this situation. So we have a signal extending from minus 2 up to 2. So computing the unilateral Laplace transform, by definition we start the integration at instant 0. So we'll be integrating from 0 up to infinity x of t e to the minus st dt. This would be x of s. Okay, so let's move to this signal over here, which is a shifted signal x of t minus tau. So we have shifted x of t to the right by 1. So x of t minus 1. As you can see, we had a non-zero part of the signal which was happening before 0 shifted right now after 0. This part specifically. This part of the signal was happening here before 0, before t equals 0, and now it's shifted to t larger than 0. So computing the unilateral Laplace transform, again integrating from 0 minus up to infinity, now this part of the signal will be included in the integration, and this will change x of s completely. So we cannot apply the time shift property in this situation, because we had a non-zero part of the signal which was happening at t less than 0, and now it is shifted to t larger than 0. This will cause a problem, and this property, the time shift property, will not hold, will not be true. Same situation over here. Imagine we have x of t plus 2, which is a shifted version of x of t, but now to the left. Now we had a non-zero part of the signal, which is this part. This part was happening at t larger than 0, and it was included in this integration. But right now, due to the time shift happening, this part of the signal now has been shifted to t less than 0. So computing the unilateral Laplace transform in this case, starting the integration at t equals 0, as a matter of fact, nothing is being integrated over here and we'll get a 0. So again, in this situation, we cannot apply the time shift property because we had a non-zero part of the signal which was shifted from t larger than 0 to t less than 0. So let's move on and try to see another example where we can actually apply the time shift property. So looking at its signal x of t over here, which is defined from instant 2 up to 4 and 0 otherwise, computing the unilateral Laplace transform, we start the integration at instant 0 up to infinity. So this is the part of the signal which is included in the integration. So let's consider y1 of t, which is a shifted version of x of t at x of t minus 1, shifted to the right. So here, computing the unilateral Laplace transform, we start from 0 up to infinity. So the entire part of the signal is now still included in the integration, and hence no non-zero part of the signal has been shifted before 0, and no non-zero part of the signal happening before 0 shifted after 0. So in this situation, the time shift property applies. Let's look at y2 of t, x of t plus 2, now shifting to the left. But still, the entire non-zero part of the signal is still happening for t larger than 0. So the integration will also include the entire signal and no non-zero part is shifted before 0. So here we can apply the unilateral Laplace transform time shift property. Here we can apply the time shift property. Let's consider the third situation, y3 of t, which is x of t plus 3, shifting to the left by 3. Now we have a non-zero part of the signal, which was happening from 2 up to 3 over here. This non-zero part is now shifted before 0. And this will cause a problem because computing the unilateral Laplace transform over here, starting the integration from 0 up to infinity, this part of the signal is not included in the integration. We had a non-zero part of the signal, which was happening for t larger than 0, now shifting to t less than 0. So here we cannot apply the time shift property. So moving back, again, here we cannot apply the time shift property, here we cannot apply the time shift property. So before applying the time shift property of the unilateral Laplace transform, you need to make sure no non-zero part of the signal has been shifted from before 0 to after 0 or the other way around. And this condition is formulated mathematically as follows. X of t minus tau times u of t should be equal to x of t minus tau times u of t minus tau. Okay. So the restriction on the shift here comes from the fact that the unilateral Laplace transform is only defined in terms of the non-negative time portion of the signal. That is the portion of the signal happening for t larger than or equal to 0. Any part of the signal which is happening for t less than 0 is not included in the unilateral Laplace transform. Hence, this property applies only if the shift does not move a non-zero t larger than 0 component of the signal to t less than 0, or does not move a non-zero t less than 0 portion of the signal to t larger than 0. So the main idea here is that if you have a non-zero part of the signal happening for t larger than or equal to 0, it should not be shifted before 0. And if we have a non-zero part happening for t less than 0, it should not be shifted for t larger than 0. If this condition is satisfied, we can apply the time shift property. Otherwise, we cannot apply the time shift property. But for causal signals x of t, and by causal signals we mean x of t is 0 for t less than 0, and for tau larger than 0, in this case the restriction or the condition we have will always be satisfied, and we can apply the time shift property in this situation for x of t causal and tau larger than 0. So here again we have an example to discuss the situation. If this is x of t, this is x of t plus 1. So we had a non-zero part of the signal which was happening for t larger than 0, now shifted before 0. In this situation we cannot apply the time shift property. And over here, if this is x of t and we had a non-zero part happening before 0, now x of t minus 1 shifted like this. This part will be shifted to t larger than 0, and it's now included in the integration. Here we cannot apply the time shift property because we had a non-zero part of the signal happening for t less than 0. Now it's happening t larger than 0. The fourth property we have is the S-domain shift. It simply says that if we know a signal x of t whose unilateral Laplace transform is capital X of s. Now, if we shift capital X of s in the S-domain by S node, which is x of s minus s node, in time domain this is equivalent to having the same x of t, but now multiplied by e to the power s node t, where s node is the shift happening in the S-domain. The fifth property is a very important property. Actually, it's called the convolution property. It simply says that if we have two signals, x of t and y of t, and x of t has a transform x of s, and y of t has a transform y of s, convolving x of t and y of t will give us, in the S-domain, multiplication of x of s and y of s. In other words, convolution in time domain is equivalent to multiplication in the S-domain. And this property actually simplifies the analysis of LTI systems very much. Because, as you remember, in LTI systems, the output is a convolution between the input and the impulse response in time domain. Applying this property, we will be having y of s, the output of the system, equal to the multiplication of the Laplace transform of the input by the Laplace transform of the impulse response, which is the system transfer function. That is, the convolution in time domain corresponds to multiplication of the Laplace transforms in the S-domain. And this property applies only if x of t is equal to 0 for t less than 0, which is a causal signal, and y of t is 0 for t less than 0, which is also a causal signal, i.e. when both x of t and y of t are causal signals. The next property is a differentiation in the S-domain. If we know a signal x of t whose transform is capital X of s, now if we do a differentiation in the S-domain, d by ds x of s, this will give us in time domain minus t x of t. So multiplying in the time domain by minus t will give us differentiation in the S-domain. That is, the differentiation in the S-domain corresponds to multiplication by minus t in time domain. Of course, all these properties has proofs, but we will not be talking about these proofs right now. It's not included in our course. Okay, so let's move on to an example and see how can we apply all these properties we have seen on this example. So in this example, we have a signal x of t, which is defined as a convolution between minus e to the 3t times u of t and t times u of t. And we need to find the unilateral Laplace transform of x of t. We need to find x of s. So let's move to our whiteboard over here. And as you can see, we have the x of t defined as a convolution between t u of t and minus e to the 3t u of t. So first we will start by remembering that the Laplace transform of e to the power at u of t is simply 1 over s minus a. So as you can see, e to the power 3t u of t is of the same form. So I can simply write down that the transform of e to the power 3t u of t is 1 over s minus 3. And similarly, we need to find the Laplace transform of t times u of t. Let's start by u of t. So u of t can be thought of as e to the power 0t times u of t. So in this case, a is 0 and the transform is 1 over s minus 0, which is 1 over s. Now we have a t multiplied by u of t, and if you remember from the differentiation in s domain property, the property said that if in time domain we have minus t times x of t, this is equivalent to differentiating the Laplace transform we have with respect to s. So here we have minus t times u of t, which means we will be differentiating 1 over s, d by ds 1 over s. So this basically will give us minus t times u of t would have the transform minus 1 over s squared. So the minus sign will cancel out, and now we have the transform of t times u of t. And since in time when we are convolving, the convolution property says if we are doing convolution in time domain, this means we will be having multiplication in s domain. So the Laplace transform of the signal x of t will simply be the multiplication of, first we have a negative sign, it will be as is, so minus 1 over s minus 3, which is the transform of this part, multiplied by the 1 over s squared, which is a transform of this part. So here, as a matter of fact, we apply two properties, the differentiation in s domain property and the convolution property, and this will be our Laplace transform, as you can see over here. So it's minus 1 over s minus 3 or times 1 over s squared. Okay, so here we have another example where we need to find the Laplace transform of the output from this RC circuit. We've seen this RC circuit in the previous chapter, and we've seen that it has the impulse response of this form, 1 over RC e to the minus t over RC u of t. So given this impulse response, and given that RC is 0.2, which means 1 over RC is 5. So basically the impulse response is 5 e to the minus 5t times u of t. We need to find the Laplace transform of the output given that the input signal x of t takes the form t e to the power 2t times u of t. So moving to our whiteboard over here, h of t is 5 e to the minus 5t u of t, and x of t is t e to the power 2t u of t. And since we have an LTI system, the output can be simply computed using the convolution between the input x of t and the impulse response h of t. But doing the convolution over here is not an easy task, since we have t e to the power 2t, it will not be easy. So now we can apply the convolution property of the unilateral Laplace transform. So y of s will be equal to x of s times h of s. And now instead of doing convolution in time domain, we will be doing multiplication in the s domain. So now we need to find x of s and h of s. So h of t takes the form e to the power at u of t, and a here is minus 5. So h of s will be 5, which is a constant we have, over s minus a, which is s minus minus 5, so s plus 5. And for x of s, it takes the form t e to the power 2t u of t. So t multiplied by e to the power 2t u of t means we will be having minus the derivative of 1 over s minus 2. So here we have applied the differentiation in s domain property, where e to the power 2t u of t has a transform 1 over s minus 2, and multiplying by a t in time domain is equivalent to minus the derivative in the s domain. So x of s will be like this, minus, and when you are doing the derivative of a rational function, we start by squaring the denominator, and then we take the derivative of the numerator, which will be 0 in this case, times the denominator minus the derivative of the denominator, which is 1 times 1 in the numerator. So now we can compute y of s very easily as the multiplication of x of s and h of s. So it will be 5 over s plus 5. This is basically h of s times x of s, which will be positive 1 over s minus 2 all squared. And this would be the Laplace transform of the output from such system. As you can see over here, 5 over s minus 5 times s minus 2 all squared. And later on, when we learn about computing the inverse Laplace transform, we will be able to find y of t in this case. The next property we have over here is a differentiation in time domain property. The property simply says that if we have a signal x of t whose unilateral Laplace transform is capital X of s, then differentiating x of t in time domain d by dt x of t will have the unilateral Laplace transform s times x capital of s minus x small, which is the time domain signal, computed or evaluated at 0 minus. So differentiation in time domain results in multiplying x of s by s in s domain, and we subtract the initial condition. Again, this is x small, the time domain signal, computed at instant 0 minus. We can think of this term x evaluated at 0 minus as the initial condition, the very first value of x of t computed at 0 minus, at instant 0 minus. We have a proof for this property. We will not go through it, we'll ignore it for now. And here we have an example we need to solve. In this example, we have a function x of t, which is e to the power at times u of t, and we need to find the Laplace transform of the derivative dx of t by dt. And let's compute this Laplace transform twice. First, using the definition of Laplace transform, and next using the property we have just seen. So let's move to our whiteboard over here, and here we have a signal x of t, which is e to the power at times u of t. So let's define another signal y of t, and y of t will be the derivative d by dt of the signal x of t. And as you can see over here, the signal x of t is defined as the multiplication of two signals, e to the power at times u of t. So in this case, in order to do the differentiation, we will need to use the chain rule. So this will simply be the derivative of the first function we have, so d by dt, e to the power at, and this will be multiplied by the second function, which is u of t, plus the first function as is, multiplied by the derivative of the second function. So moving on, y of t will be given as, so the derivative of e to the power at is a, e to the power at, and then we multiply by u of t, plus the first function e to the power at multiplied by the derivative of u of t, which is an impulse delta of t. As you can see over here, if we have a unit step u of t, the derivative of this function will be like this. So in this part we have 0 value for all time less than 0, so the derivative here is 0. And for this part, we have a constant which is also has the derivative of 0. But at this instant 0, we have a sudden change. Sudden change means in no time we have a change of value from 0 to 1. So delta y is 1, delta x is 0, which will give us sort of an impulse over here. So the derivative of u of t is an impulse delta of t. So over here we have an impulse multiplied by a function, and this basically will give us the value of the function at the impulse. So here we can write y of t as follows. So y of t would be a e to the power at times u of t plus computing the value of the function e to the power at at instant 0. E to the power 0 is 1 times delta of t, so we'll be having an impulse whose weight is 1. Now we can compute the Laplace transform of y of t. So the first term, a e to the power at times u of t, a is a constant. E to the power at u of t will have the Laplace transform 1 over s minus a. So we can write y of s as a over s minus a plus the Laplace transform of an impulse delta of t. So how can we compute the Laplace transform of the impulse delta of t? The definition is very straightforward. It is the integration from 0 minus up to infinity the function we have, which is delta of t e to the minus st dt. And here, since the integration of 0 minus starts at 0 minus, so the impulse will be included in the integration. And as we have seen in the previous chapter or the chapter before, integrating an impulse multiplied by a function will give us the value of the function computed at the impulse. So here we have an impulse happening at instant 0 multiplied by a function e to the minus st, which will give us e to the power 0, which is 1. So y of s would take the form a over s minus a plus 1. Now combining these two together, so y of s would be a common denominator s minus a and a plus s minus a, which will give us s over s minus a. And this would be the Laplace transform of y of t, which is a derivative of x of t. And here we have used the direct definition of the Laplace transform. Next, let's compute the Laplace transform using the property we've just seen. So here we have a function e to the power at times u of t, and we know the unilateral Laplace transform has the value 1 over s minus a. Now the property says if we have the derivative of a function that we know in time domain, the unilateral Laplace transform would be simply multiplying this x of s that we know, which is 1 over s minus a. It should be multiplied by s. And next we need to subtract the value of x small, the function we have evaluated at instant 0 minus, where this is the function x small we have. This is our x of t. So what is the value of x of t computed at 0 minus? So moving on over here, x of t is a multiplication of two functions, e to the power at times u of t. So let's take a closer look at u of t, which has a sudden change at instant 0. But just before 0, at 0 minus, the value of u of t is 0. And just after 0, at 0 plus, the function takes the value of 1. From here we can conclude that the function x evaluated at 0 minus will be 0. And in this case we can write y of s as s over s minus a minus 0, which is exactly the same form we found when we computed the unilateral Laplace transform using the definition. So here s over s minus a, and here s over s minus a. So here we understand how to apply this property of the differentiation in time domain. We multiply by s and subtract the initial condition. The differentiation property can be generalized to higher order derivatives as follows. So if we have an nth order derivative of x of t in time domain, this corresponds to multiplying x of s by s to the power n. And we need to subtract the initial conditions as stated over here. But for simplicity, we'll assume that all initial conditions are zeros, and this will be the situation in our problems. So this property will be simply, if we have an nth order derivative of x of t in time domain, then we will multiply x of s by s to the power n. So a second derivative in time domain means we have s squared times x of s. A third order derivative in time domain means we have s cubed multiplied by x of s. This will simplify dealing with differential equations and systems which are described using differential equations, because we'll be transforming differential equations into ordinary equations and solve them in S domain, and then we can go back to time domain. So next property is the integration property. I will be skipping this property, and property after is the initial and final value theorems. Also I will be skipping those, and this will be it for today's lecture. In the next lecture we'll start talking about the inversion of the unilateral Laplace transform.